Welcome to the deep dive.
Glad to be here.
Today, we're really zoning in on a specific and I think pretty crucial concept in computer science. It's all about handling something called hash collisions.
Right, when you're using hash tables, which are, well, everywhere.
Exactly. These tables are amazing for speed storing data, getting it back fast, but they have this built-in challenge. What do you do when two different things want to go in the exact same spot?
Yeah, that collision. It's fundamental.
So our source material for this is an excerpt from Hello Algo, specifically section 6.2, hash collision.
A good, clear explanation.
We're going to unpack why these collisions happen. Spoiler, they're pretty much guaranteed. Then we'll look at the main ways developers tackle them.
The two big strategies, yeah. Separate chaining and open addressing.
We'll get into the pros and cons, the trade-offs you make with each, and then crucially, see how this stuff actually shows up in languages you might use every day, like Python or Java.
It's like getting a backstage pass to see how efficient data storage really works. Hopefully by the end, you'll have a really solid, almost intuitive feel for this, something that sticks.
Okay, let's start with the problem itself. Why are collisions, as the source puts it, basically inevitable?
Well, it comes down to a numbers game, a fundamental mismatch, really. Think about all the possible keys you could ever put into a hash table, like every possible username, every product ID, whatever it is.
That input space is huge, potentially infinite or near enough.
Exactly. But the hash table itself, the array where you actually store things, that's finite. It has a fixed number of slots or buckets, maybe thousands, maybe millions, but always a finite number.
So you're trying to map this enormous set of possibilities
Into a much, much smaller set of storage locations.
It's like the library analogy you mentioned earlier, millions of books, only a few hundred shelves. You use a rule, your hash function, to assign books to shelves.
And inevitably, different books are going to end up needing the same shelf. It's just math. Your hash function takes a key and spits out a bucket index. With way more possible keys than buckets, multiple keys have to map to the same index eventually.
Collisions aren't a mistake then, they're expected.
They're an inherent consequence of the design.
And the immediate headache they cause. You search for something, you get to the right bucket, but oops, there's more than one thing there.
Right. How do you know which one is yours?
Yeah.
Or worse, maybe the thing you added got overwritten by something else that hashed to the same spot. That leads to incorrect results, which is obviously bad.
So the simplest idea might be, okay, collision, make the table bigger. Does that work?
Well, you do resize hash tables
Right.
when they get too full overall to maintain performance. But using resizing to solve every single collision as it happens, no way.
Why not? Just sounds like a lot of work.
A huge amount of work. Imagine.
Yeah.
Collision happens. You decide to double the table size. Now you need to allocate a whole new, bigger array. Then you have to go through every single item already in the old table, recalculate its hash based on the new table size because the index will likely change, and then move it to its new spot.
Oh, wow. That sounds incredibly expensive, especially if collisions happen often.
It is. It's a major operation. So resizing is for managing the load factor, the overall fullness, not for handling individual collisions on the fly. We need smarter, localized strategies for that.
Which brings us to the two main approaches the source details.
Exactly. Separate chaining and open addressing. These are the core techniques you need to understand.
Let's tackle separate chaining first. What's the philosophy here?
The core idea is pretty intuitive, actually. Instead of forcing a bucket to hold only one key value pair.
You let it hold more.
Right. Each bucket in the array doesn't just hold the data itself. It holds a pointer to some other data structure, typically a list. Think of it like a little chain hanging off each bucket slot.
Like figure 6.5 in the source shows. An array and then little lists dangling off some entries.
Precisely that visual. So if multiple keys hash to index 5, they all just get added to the list that's associated with bucket 5.
Okay, so how do the operations change? Querying, for example.
Simple enough. You hash your key. That gives you the bucket index. You go to that bucket, find the list attached to it, and then you just walk down that list.
Comparing keys as you go.
Exactly. You compare the key you're searching for with the key of each item in the list. If you find a match, great, you return the value. If you hit the end of the list without a match, the key isn't there.
And adding a new item.
Same start. Hash the key, find the bucket, go to its list. The source mentions a common check here. You might first traverse the list to see if the key already exists.
To update the value instead of adding a duplicate?
Right. If it's already there, update the value. If it's not found, just append the new key value pair to the end of the list.
And deletion seems like it would follow the same pattern.
It does. Hash the key, find the bucket, Traverse the list, find the node with the matching key, and then just remove that node from the list using standard list deletion logic.
Conceptually, that feels quite clean. But the source points out limitations. What are they?
Two main ones. First is space. Those lists take up extra memory. If you use linked lists, each node needs pointers. Next, maybe previous. If you use dynamic arrays, there's some overhead there too. It's not just the key value pairs anymore.
So potentially more memory usage overall. What's the other drawback?
Performance, specifically when collisions become frequent for a particular bucket. If your hash function isn't great, or just by bad luck, one bucket might end up with a really long list attached to it.
And searching that long list
Becomes slow. Instead of the near-instant O1 lookup we want from a hash table, you're now doing a linear scan ON along that specific list. Where does the list like? In the absolute worst case, if everything hashed to one bucket, your hash table just turned into one giant linked list.
defeating the whole purpose. Okay, but there's an optimization for this, right? For those really long chains.
Yes, and this is where practical implementations get clever. The source mentions this, and it's common in real systems. If a list within a bucket grows beyond a certain threshold, say 8 items,
You do something different.
you convert that specific list into a more efficient structure, typically a balanced binary search tree, like a red-black tree or an AVL tree.
Oh. So you switch from an ON list search to an O-log-n tree search for just that one overloaded bucket.
Exactly. It's a fantastic optimization. It contains the damage of lots of collisions in one spot, keeping the worst-case lookup time logarithmic instead of linear for that bucket, while the rest of the table still enjoys O1 average performance.
That makes a lot of sense. It's like adding a turbocharger just where you need it.
Precisely. The source notes that its basic code examples use dynamic arrays for simplicity, not linked lists, but the principle holds. And those examples also include resizing logic based on the overall load factor, like expanding when it hits 23 full, which helps keep the average list lengths short.
Right, resizing the whole table helps prevent most lists from getting long in the first place.
Correct. That combination, resizing for overall load and maybe tree conversion for extreme cases, makes separate chaining very robust.
Okay, that's separate chaining, adding extra structures within buckets. Now, the second strategy, open addressing. This sounds like it takes a different path.
Completely different philosophy.
Yeah.
Open addressing says no extra lists, no extra trees attached to buckets. We're going to store everything directly in the main hash table array itself.
But what if the spot is already taken? That's the collision problem.
Right. So if the spot your key hashes to is occupied, you don't add a list. Instead, you start probing, looking for the next available empty slot somewhere else in the array according to a specific pattern.
Probing. Like searching around.
Exactly. You probe or search for an empty bucket. The simplest way to do this is called linear probing.
Okay. Linear. Sounds
Yeah.
like straight line.
Hash your key, get index I. If bucket I is full, you check bucket I plus 1. If that's full, check I plus 2, then I plus 3, and so on. You just step forward one slot at a time.
What if you hit the end of the array?
You wrap around. Treat the array like it's circular. So after last index, you check index 0, then 1, and so on. You continue this linear probe until you find an empty slot, and that's where you insert your key value pair.
Okay, insertion makes sense. Find the initial spot. If full, walk forward until empty. What about searching?
You follow the exact same path. Hash the key to get the starting index I. Check bucket I. Is the key there? If yes, you found it,
What if bucket I has a different key because of a collision during insertion?
then you know you need to probe. You check I plus 1, then I plus 2, following the same linear sequence. You keep going. If you find your key along this path, great.
And if you hit an empty slot during the search,
Then you stop. An empty slot tells you the key you're looking for cannot be in the table. Because if it were in the table, the insertion process would have placed it in one of the slots you just checked before you hit this empty one. The empty slot breaks the potential probe chain.
got it. Figure 6.6 shows the scattering effect, right? Keys that hash together get spread out into nearby empty slots.
Exactly. It seems efficient in terms of space, maybe. You're not using extra memory for list pointers.
True, but the source highlights a major drawback, especially for basic linear probing. What is it?
Clustering. It's a big one. As you insert items, occupied slots tend to clump together into contiguous blocks.
Like traffic jams on a highway.
Good analogy. And the problem is, once a cluster forms, it tends to grow. Any new item that hashes into that cluster, or even is before it, will have to probe further and further, likely adding to the end of the cluster, making it even longer.
So probe sequences get longer, meaning insertions, searches, and deletions all slow down.
Significantly, yes. especially as the table gets more full. Performance can degrade badly due to this primary clustering effect.
Okay, clustering is bad, but then there's this other really tricky issue with open addressing: deletion. The source makes a big deal about this. You can't just remove an item and leave the slot empty.
You absolutely cannot. This is maybe the most counterintuitive part of open addressing. Think about that search process we just described.
Okay, hash, probe until key found or empty slot hit.
Right. Now imagine you inserted key A at index 10. Then key B came along, also hashed to 10, collision, probed forward, and landed in index 11. Then key C hashed to 10, probed past 11, occupied by B, and landed in index 12.
Makes sense. A chain: 10A, 11B, 12C.
Now what happens if you delete key B from index 11 and just mark slot 11 as empty?
Uh-oh.
Uh-oh is right.
Yeah.
Now if you search for key C, you'll hash to 10, find A, not C, probe to 11, and find an empty slot.
And the search stops. It incorrectly thinks C isn't in the table, even though it's right there at index 12.
Exactly. Simply emptying the slot breaks the probe chain for any items that were inserted after it due to collisions. Figure 6-7 shows this perfectly. Deleting one item makes others inaccessible.
Wow. Okay, so how do you delete in open addressing? You must be able to delete things.
Use a technique called lazy deletion. Instead of making the slot truly empty, you mark it with a speckle placeholder value. The source calls it a tombstone.
A tombstone. Okay,
Yeah.
What does that signify?
It signifies this slot used to contain an item, but it's been deleted. Now, how does this affect operations?
Let's see. For insertion.
For insertion, a tombstone slot is treated just like an empty slot. It's available. You can overwrite the tombstone with your new key value pair.
Okay, that's simple. But for searching.
This is the key difference. When you're searching and you encounter a tombstone, you cannot stop. You have to treat it as occupied for the purpose of continuing the probe.
Because the item I'm looking for might be further down the chain past this deleted item's old spot.
Precisely. You must continue probing past any tombstones until you either find your key or hit a truly empty none or null PTR slot.
Okay. Lazy deletion with tombstones solves the correctness problem, but it feels like it could create another issue. If you delete a lot, won't the table fill up with these tombstones?
It can, yes. That's the downside. While tombstones allow new insertions, they don't shorten probe sequences for searches. A search might have to step over many tombstones, slowing things down over time, even if the table isn't actually full of active data. Performance degrades.
So, lazy deletion fixes one problem, but potentially worsens performance gradually. Is there anything to mitigate that?
Yes, the source mentions a neat optimization. During a search, keep track of the index of the first tombstone you encounter in your probe sequence.
Okay.
If you later do find the key you were searching for, further down the probe path, you can perform a swap. Move the found key value pair into the location of that first tombstone you passed, and place a tombstone where the key originally was.
So you're effectively moving frequently accessed items closer to their initial hash position, bubbling them up past the tombstones?
Exactly. It uses the search operation itself to gradually clean up the tombstones and improve the layout for future searches of that item. It's quite clever.
The code examples in the source for open addressing reflect this complexity, right? Circular array logic, the tombstone marker, handling it in searches, and maybe even that swap optimization.
Yes, they demonstrate the core logic needed to make open addressing work correctly, including handling deletions without breaking searches.
Now, linear probing isn't the only game in town for open addressing. The source mentions others.
Briefly, yes. There's quadratic probing. Instead of stepping forward +1, +2, +3, you step forward using quadratic increments. +1 outer ends, +2 inners, +3 inners. So +1, +4, +9, +16, and so on.
What's the goal there?
To alleviate the primary clustering problem of linear probing, by jumping further, it tries to spread colliding items out more, avoiding those long contiguous blocks.
Does it work perfectly?
It helps, but it can suffer from a milder form called secondary clustering, where keys that hash to the same initial spot still follow the same quadratic probe sequence. Also, depending on the table size, quadratic probing isn't always guaranteed to find an empty slot even if one exists.
Okay, so better than linear, maybe, but not perfect. What else? Double hashing.
Right, double hashing uses 2 or potentially more different hash functions. The first hash function gives you the initial bucket index. If that's full, use the second hash function on the key to determine the step size for your probing.
So the jump size isn't fixed like +1 or +i. It depends on the key itself via a second hash.
Exactly. Hash 1 key gives the start. Hash 2 key gives the step size s. You check index start +s, then start +2, start +3s, and so on, all modulo the table size, of course.
That sounds like it would be much better at avoiding clustering, since different keys hashing to the same spot would likely have different step sizes from the second hash function.
Generally, yes. It provides better distribution and avoids the clustering patterns of linear and quadratic probing more effectively. The trade-off.
More computation, calculating two hash functions instead of one.
Potentially, yes. It can be slightly more computationally expensive per probe step.
And the source reminds us that tricky tombstone lazy deletion issue applies to all these open addressing methods, right? Quadratic, double hashing, whatever.
Absolutely. The fundamental problem of needing to preserve probe chains during deletion is inherent to the open addressing philosophy itself, regardless of how you calculate the probe steps.
Okay, deep breath. That's a lot on the mechanics. Separate chaining, list trees and buckets. Open addressing, probing in the main array with tombstones. How does this translate to the real world? What do popular languages actually do?
The source gives some great examples showing these aren't just theoretical ideas. Let's start with Python. Everyone uses Python dictionaries. Dict.
Yeah, fundamental. What's under the hood?
Python's dict uses open addressing.
Oh, interesting. Which kind?
Not simple linear or quadratic. It uses a more sophisticated method where the probe sequence is generated using pseudo-random numbers derived from the key's hash. It's designed specifically to break up clustering patterns very effectively.
Clever. Okay, what about Java? Its hash map.
Java's hash map is a classic example of separate chaining.
With lists.
Primarily, yes.
Okay.
But it famously includes that tree optimization we talked about. Since JDK 1.8, if a chain list in a bucket gets too long specifically, 8 elements and the whole table is sufficiently large, at least 64 slots, Java dynamically converts that single list into a balanced red-black tree.
Wow, so it actually implements that O-login and fallback for busy buckets. That's concrete.
Absolutely. It's a practical solution to handle potentially bad hash distributions gracefully. And if items are removed and the tree size shrinks below a threshold, like 6, it converts back to a list to save the overhead of the tree structure.
Fascinating. And Go, its map type.
Go also uses separate chaining, but with its own distinct flavor. It has a limit on how many key value pairs, up to 8, are stored directly within the main bucket structure.
What if it needs more than 8?
Then it starts linking to overflow buckets. So a chain can consist of the main bucket plus one or more linked overflow buckets. If a chain gets too many overflow buckets, Go may trigger a specialized resizing operation.
So, similar core idea, separate chaining, but different detailed implementation choices.
Exactly. Python chooses sophisticated open addressing. Java uses separate chaining with tree conversion. Go uses separate chaining with overflow buckets. It shows there's no single best way. It depends on the language designer's goals and trade-offs.
Okay, let's try to pull this all together then. We've gone deep into why hash collisions happen and the two main ways to deal with them.
Separate chaining think lists or trees hanging off buckets. Generally simpler logic, especially for deletion. But potential space overhead per bucket and the risk of slow list traversals if a list gets very long without optimization.
And open addressing finding an empty slot in the main array via probing can be more space efficient in the array itself, no extra pointers per se, but much trickier deletion requiring tombstones and the constant battle against clustering degrading performance.
Right. Different trade-offs.
So for you listening, maybe writing some code using a dictionary or a map, why does drilling down into this level of detail matter?
Because it fundamentally explains the performance characteristics you observe. It tells you why these data structures are usually incredibly fast. O1, average time for lookups, insertions, deletions. That happens when the hash function works well, and collisions are minimal and handled efficiently by either chaining or probing.
But it also explains why, sometimes, maybe in hedge cases or with unlucky data, an operation might suddenly seem slower.
Exactly. That slowdown could be traversing a long chain in separate chaining, or following a long probe sequence past many occupied slots or tombstones in open addressing. Understanding collisions and resolution gives you insight into both the average and the potential worst-case behavior. It's not magic. It's these mechanisms at work.
Knowing this helps you appreciate why certain operations cost what they do, and maybe even helps in thinking about how your own data might interact with these structures. It's foundational knowledge for efficient programming.
Absolutely. It demystifies a core part of how software manages data quickly.
Well, that wraps up our deep dive into hash collisions, a really important concept baked into so many systems we use.
Definitely worth understanding. And it leads nicely into one final thought, something the source touches on but is critical.
Which is?
Spent all this time talking about how to resolve collisions. But the effectiveness of any resolution strategy is massively dependent on the quality of the hash function itself.
Ah, right. If the hash function is terrible, it doesn't matter how clever your collision handling is, you're going to have a bad time.
Precisely. A bad hash function might dump tons of different keys into just a few buckets. That creates huge lists for separate chaining or massive clusters for open addressing right from the start, overwhelming the resolution strategy.
So the first line of defense is actually choosing or designing a hash function that distributes keys as uniformly and randomly as possible across the available buckets.
Yes. Minimizing collisions in the first place is just as important, if not more important, than handling them well when they inevitably occur. It's a two-pronged challenge for developers.
Designing good hash functions and choosing the right collision resolution strategy, a constant balancing act.
That's the essence of building high-performance hash tables.
Thank you for joining us on this deep dive. We hope this exploration gives you a lasting grasp of hash collisions and how they're managed.
Keep digging into these fascinating data structures. There's always more to learn.